we are going to discuss cart clothing today. Cart clothing means that the bare cylinder, the duffer, the lingering, these elements of the carding machines needs to be completely clothed with large number of pins or teeth, and hence the term clothing has come, the way we dress ourselves. Cart clothing could be of two types, flexible and rigid. So, depending upon the organs, we decide which type of clothing should go to that particular organ. We can see, if we study a machine, we will find the large number of short tooth type of teeth or pins on surfaces of lingering, cylinder, flat, duffer, and also on pre and post carding segments. We will first discuss lingering clothing. Lingering clothing, we have strong metallic wire points on the surface of the lingering. The tooth of a given profile is cut into a rolled wire by a high precision cutting tool. Cutting is immediately followed by hardening. The important parameters of the wire or the tooth are its height, width of its base, angle of inclination between a line normal to the base of the tooth and the leading edge alpha, and the tooth density, that is T, which is teeth per inch. Here we can see in the diagram the profile of lingering tooth as well as its specifications, that is height, width, the inclination angle alpha as shown in the diagram, and the number of teeth per unit length. Generally, what we see is that the heights of the teeth are 5.5 millimeter, the width of the base is around 12, not 12, sorry, 1.5 mm, and the number of teeth per unit length varies between 3 to 5. To clothe the lingering, 4 to 8 helical grooves are cut into its surface, each having a lead of 1 inch. We can see it in the diagram, the helical grooves shown by different colors. So, if we have a 6 inch start, 6 start lingering, then we will have 6 parallel grooves 1/6 of an inch apart. In the present case, we can see there are, the start is 4, that means in an inch there are 4 grooves which are cut. Now, the metallic wire is then forced into the groove during the winding operation on the lingering. The tip distribution over the surface becomes more homogeneous with more number of starts. If G stands for lead between two adjacent windings, regardless whether single or multi start, and small t as shown is the pitch in millimeter, the tooth density will be T d is 100 by small t into G. The typical tooth density on lingering could be between 25 to 40 per square inch. The lifetime of a lingering wire is about half of that cylinder and duffer. The nature of wear on the wires is such here the wire means the tooth or the pins on it, that these wires cannot be ground to bring them back to normal working again. Hence, they need replacement when damage is beyond repair. So, the lingering teeth are much robust in nature, because they have to tease out the unopened tuplets that we are feeding to the machine. Hence, they are much stronger in comparison to the kind of teeth which are used on cylinder, flat or Deferred. From Likarian clothing we go to now flat clothing. Flat clothing is flexible in nature. What does it mean flexible? That the pins which are there, they can easily bend. That is why they are flexible. Now, here long pins having round or oval cross section shapes are inserted into a backing. These pins are bent into a U shape along with a knee as shown in the diagram. That the knee is here, here is the knee. Pins are inserted into an elastic backing made of 5 plies of cloth. So, this is the cloth on which the pins are inserted, and these plies are joined together by vulcanizing. This permits the points to bend easily under the influence of stress beyond a certain limit, that whenever the force, the opening force will be acting on these pins, the pins can easily bend. That is the advantage that we have. And why do you need this flexible part points on flats or flexible teeth on flats? Fibers will experience intense force while getting carded between cylinder and flats. If the flat wire points can bend, when the carding force becomes excessive, then the stress level on the fiber will reduce, and therefore, the damage to the fibers can be avoided. That is the reason why we need flexible pins on flats. The pins on cylinder are quite rigid in nature. The other questions that may come to our mind is why the pins need to be bent. Now, here in the diagram we see that the diagram, first diagram, a pin is shown by a line, and let us say this has no knee, it is a straight pin going from here to there. And in the other case we see a pin which is bent at the knee here and going up to this point. Now, if a force acts on it because of the carding action, the pin is going to move. When this pin moves along the arc shown here, and if it comes exactly on the top of its base, the rise in height in this case is going to be around x2, because this will move in an arc whose radius is going to be like in this case O, let us say A, this point. It will move along an arc with the radius OA, whereas in the second case, if this is O, this is A, let us say this is B, represents the knee point. In this case, if a similar force acts on the pin, it will also move in an arc, but the arc will have a radius equivalent to AB, and therefore, if we compare the rise in height in both the cases, then we will see the rise of tip of the straight wire point or straight tooth will be much greater than the rise by similar tooth with bent knee, that is x2 is greater than x1. These rise may even cause the pins of the interacting surfaces to collide, that is, when the cylinder and the flat pins are interacting together, on fibers, if the rise of the pins are too much, there is a chance that the tip of the flat teeth will collide or will come into contact with the teeth of the cylinder, and therefore, they might get damaged. This we want to avoid. So, the knee will ensure limited rise of the wire point. So, wire point and tooth are basically same. In the industry, the wire point term is more frequently used. So, the wire point with knee will ensure limited rise when strained by the carding force, and hence the possibilities of collision between the metallic teeth of the cylinder and flats can be avoided. Now, there are semi rigid clothing on flats are also available. Now, why semi rigid clothing, or what could be the problems with flexible clothing? Now, flexible clothing with knees get choked with fibers very quickly. This is a problem, because during carding action, part of the force will force the fibers to move along the base or towards the base of the wire point, and as a result lot of fibers will go and accumulate near the base, and hence it gets choked or gets filled up with fibers very quickly. So, that will gradually reduce the opening capability of the carding action, and hence so much flexibility may not be good, especially with high production carding machines. Now, here what we do, the teeth are not so flexible, they are semi rigid in nature. Now, for this the backing contains 7 or more plies of cloth and plastic layers resin bonded together. The base becomes stronger and does not yield easily. So, here this is the base, and there are 1, 2, 3, 4, 5, 6 or 7 layers of cloth as well as some plastic, some resins. So, the teeth are inserted here, and therefore, the base become relatively rigid in comparison to what we have in the case of flexible clothing of flats. See, the base does not yield easily, the rise of the tip point will be less. Then in this backing we insert the teeth as we have done in the previous case. So, these diagrams are showing how the teeth will look like inside the base. The wire points are made of carbon steel with 0.6 to 0.6% of carbon. So, the carbon steel will make it very resistance to abrasive forces or abrasive actions, because the pins will be continuously acted by the fibers. So, there is always lot of abrasion which is going on between the fibers or the teeth, and with time the teeth will get damaged, and hence we need to make sure that the teeth are made by such material which can resist the abrasive forces of the fibers. Now, the cross-sectional shape of the tooth. The flat wire points or flat teeth are generally of two basic shapes, double convex or elliptical type or rectangular. These are the two types of shapes. So, one is something like this, and other one is something like this. So, this is rectangular and this is elliptical in nature. For elliptical wire, the major axis remains in the direction of the material flow, another important point, and for rectangular wires the length faces the material flow directions. So, material flow directions shown by these arrows. So, this is the direction in which the teeth will be actually placed into the base of the flats. In the case of flat wire cross section, sharpening operation broadens the working surface of the point tip and hence reduces its effectiveness. Therefore, flat wires can be sharpened only once or twice. However, with lateral sharpening it can be carried out more number of times. This is why flat wire points cannot be sharpened too many times, and in comparison to what we can do with cylinder or Deferred wire points. Now comes the setting pattern. How when the pins or the teeth are inserted, then what kind of pattern it takes. There are 4 type of patterns which could be there. Plain twill setting, pattern number 1, that is, if we concentrate on the tip of the teeth, then we find that they are following a twill setting. Here what is going to be advantage or disadvantage with this? Varying point densities when the surface is examined in smaller segments. So, this is what is a disadvantage with the plain twill setting. Then it comes staggered twill setting. The twill is broken after every 3 staples to be offset by half the staple, and it gives more uniform distribution of the pins on the surface of the flat. The other one is progressive point density. The points on an individual flat top are distributed in 2 sections, one with wider and the other with closer point density. That is, part of the same flat, part of it will have higher point density, the other part will have lower point density. The point density which is less will face the incoming fibers. As a result, what happens? Points with wider spacings are supposed to act on large trash particles and fiber tubs, and narrower spacing provides intensive action on remaining finer tubs and naps. So, basically by having this progressive point density, we try to achieve a gradual increase in intensity of the carding action over a particular flat also. At the same time, the larger trash particles will find spaces to get lodged in between the spaces where the point density is less. The point density is too high and the space is smaller than the size of the trash particle, then the trash particle will not be able to penetrate or get into the teeth, and hence they will not get lodged and will move forward. So, that is the possibilities which are there if the point densities are exactly same all over the flat. And that could be combination setting, which is a combinations of the 2 that we have discussed earlier. This would mean to deliver the advantages of both. So, this could be also there. So, these are the different types of patterns that is followed, and here in this table we see the flat wire points geometrical parameters, that is its height, the angle at which they are inclined, and the point densities. What we see here, depending upon the type of fiber that we are going to process, the height, angle and the point density is are to be changed. That is what is recommended by the machine manufacturers. So, what is important to see here, that the height is more or less constant, which is close to 8 millimeter. The angle of inclination is 70 to 80 degree, and the point densities may range between 330 to 520 degree, 520 points per square inch for long and fine cotton, but if we go for synthetics or if we go for short Antarctic cotton, the values are close to 270 points per square inch. PPSI stands for points per square inch and PPCM stands for points per square centimeter. So, we can say that all these important parameters of the wire points which are found in the flats of today's carding machines. After discussing the flat wire points, we will now move to cylinder and Deferred clothing. What is special about cylinder clothing? Now, these wire points should be designed in such a way so that there is lesser tendency to load by fibers. So, the height, the angle and the thickness, all these have to be designed in such a way that the cylinder wire point should not get loaded by fibers, that the fibers should not get lodged in between the spaces of the teeth which are there on the cylinder. There has to be high efficiency of fiber transfer from cylinder to Deferred. This point also we have to take care of, and the last point is the longer life, that is they should not get abraded too fast also, or they should not get bent easily. These are the important requirements of the cylinder clothing. The other thing is easy transport of fibers from cylinder to Deferred, since fibers remains on the teeth surface. The way the clothing is designed, we will see that the fiber transfers becomes easy from cylinder to Deferred, because most of the time the fibers will remain on the surface of the teeth. There will be lesser tendency to get loaded with fibers also, and we need infrequent grinding. The way we choose the material part of the wires, that they will not get blunt too fast, and it must have a longer life, as has been told earlier. So, these are the important points that we have to remember. Keeping in mind these requirements, the cylinder clothing is all metallic in nature and they are rigid also. So, they are not flexible like we have seen in the case of flats. Now, what are the clothing parameters? A typical teeth is shown in the diagram, and there are so many parameters, geometrical parameters, which will define the complete geometry of the teeth that we have on cylinder or Deferred. Geometrically they are very similar to each other. So, what are the parameters? There is a base width A1, there is a tooth thickness A2, tooth thickness at the tip A3, overall height is H1, height of the base is H2, depth of the tooth is H3, tooth pitch shown here is small t, carding angle is this angle which is alpha, and wedge angle, that is this angle which is gamma. So, there are so many parameters are there which will actually define the tooth geometry of slender or Deferred wire points. Now, if we try to see the geometry carefully, then we can establish the relationship between the geometrical parameters of tooth. So, in the diagram a simple profile is shown with the necessary parameters, like here is the profile of the tooth and we have a carding angle alpha, then back angle called beta, wedge angle which is gamma, depth of the tooth is h and the pitch is t. Now, if we see this diagram and then we can establish the following relationship. First of all, tan alpha is d by h, hence d is h tan alpha. Tan beta is h by d plus t, and the summation of alpha, beta and gamma is 90 degree, because if this is angle beta, then this angle is also going to be beta, and therefore, sum of alpha, gamma and beta is always going to be 90 degree. So, alpha, beta, gamma are actually bound together and the sum of them has to be 90. So, from here if we try to find out what is the pitch t, then we can write that t is h by tan beta minus d, or if we take the relationship, put the value of d from equation 1, then we can write t is h cot beta minus tan alpha, where h is the common. So, this is how the angles, the pitch and the height of a tooth are connected together, and these simple equations can help us to understand that if we want to change point density or if we want to change some other parameter, what will happen to the other parameters. A reduction in pitch t, and if we want to have more teeth per unit length of the wire, so that we want to increase the point density, that is number of points per unit area, then this will mean a decrease in h, height has to go down immediately, while alpha and beta remains unchanged. That is, if we want to keep the alpha unchanged, beta also unchanged, because alpha is going to affect the intensity of the carding process, but without compromising alpha, if we want to have more and more pins on the surface, then one way of doing this is to reduce t, and while doing so we have to reduce basically h. That means basically if I want to do this, if I draw a line parallel to this, the front face as shown by this diagram, then obviously the height is going to be here. So, height h is going to go down, now it will be less, and obviously in this case the t will go down. So, t will reduce, but simultaneously height is also going to reduce. At the same point height, it is also possible by increasing alpha or by decreasing beta, that also is possible. Therefore, in that case, if we want to do not want to change the height, we have to keep it constant, then we have to play with alpha and beta. Significance of the clothing parameters. Let us say pitch. A reduction in pitch T will increase basically point density, that is the purpose to play with T, but tooth height will decrease as shown by the previous equations. Points per square inch or the point density can be given by this simple equation. It is 645 by base width and pitch as shown in the equation. How the value 645 is coming? 645 is nothing but 2.54 into 2.54 into 100 or 254, 25.4 and 25.4, that is 1 inch, that is in centimeter 2.54, another inch in the cross directions and 1 inch in the length directions is this centimeter, and if we convert them into millimeter, we have to multiply it by 100. So, if we do this, this value will be 645. So, 645 by the base divided by the base width multiplied by the pitch will give you the points per unit area, where the unit is expressed by inch. The carding angle alpha. This angle actually decides the intensity of the carding actions and the transfer efficiency of fibers from Slandered to Deferred. The carding angle alpha and the inclination angle beta. The inclination angle, this beta is inclination of the back edge of the tooth, it is 90 degree minus carding angle. With lesser carding angle or more inclination angle, that is if you reduce alpha, fiber transfer is facilitated, whereas carding intensity will reduce. And if we go for lesser carding angle, then fiber transfer will be more from Slandered surface to Deferred, because the holding power of the Slandered tooth on the fibers will be less, and hence their transfer from Slandered odd points or Slandered tooth to Deferred tooth will be little easier. The carding angle may be positive or negative or neutral, that is 0, depending upon the situation, but generally it is not equal to 0. Typically, the carding angle of Slandered and Deferred are shown now in this table. The Slandered, it varies between 10 degree to 40 degree, and the Deferred, it varies between 20 degree to 40 degree. It is not minus 40, this is plus 40. Sometimes we go for negative angle, but this negative angle is chosen in the case of Licarin tooth, because when we need to process synthetic fibers, then we want to go for negative angle, because in that case the Licarin will facilitate transport of fibers from Licarin teeth to the Slandered easily. Synthetic fibers are generally long and their friction in the teeth is also much more in comparison to what we find in the case of cotton. Therefore, to facilitate their transfer from Likkanen to cylinder, we go for negative rake angle of the Likkanen teeth. At the same time, the negative rake angles will also help in reducing the stress level on the fibers. That also, especially when the fibers are too weak or very fine, then also we may go for negative rake angle, but generally the negative rake angle we go for synthetic fibers, and that too only for Likkanen, not for cylinder and Deferred. A lesser carding angle facilitates ejection of trash. That is the advantage we may get, that the trash particles can easily escape from the teeth towards the flat wire points when the angle is less. The other important point is, with higher carding angle, a smaller flat surface at the tooth tip is created for same depth of grinding, and hence it impairs carding capacity. Now, this point we are going to study now, what is the role of carding angle in creations small flat surface at the tooth tip while we are grinding our teeth. See, the teeth of the cylinder and Deferred needs to be sharpened time to time. So, there is an interval of sharpening actions with processing of fibers over a certain period of time. The teeth will get abraded. So, we need to then grind it, and in the grinding process there is a little reduction in height. We will see that, and that reduction will lead to what? That question comes to the mind. Let us look at this diagram and try to understand what happens when you go for grinding actions. We will see that we will come to that point little later. Let us first now discuss the height h and its role. Height has a strong influence, height of the tooth, on carding intensity and transfer efficiency in the case of cylinder clothing. Lesser the height, more difficult it becomes for the fibers to escape carding action. This point is important, because whenever the forces are acting on the fibers, fibers will have a tendency to move towards the base, and if there is sufficient space available, they will go and settle there. So, these possibilities can be reduced if we do not allow space to be there, and hence lesser the height, lesser will be the pace, and therefore, the proportion of fibers which will remain near the tip of the wire point will be more if the tooth height is reduced. Therefore, with shorter tooth height, intensity of the carding action will be much more intensive, because whatever fibers are held by particular tooth, most of it will be exposed to carding action, and the little part of those fibers held by particular tooth will be towards the base and will escape carding actions. Short tooth will also facilitate transfer of fibers to Deferred. There is another important thing that it can facilitate, because most of the fibers will remain on the top of the tooth or pins. The other important thing is height will also influence the point density, which was discussed earlier, that if we want to increase point density, we have to reduce the height. Overall height of the cylinder and Deferred and other parameters of the tooths are shown here. What we find, we compare these parameters between cylinder and Deferred, then we see that height for Deferred wires are generally more than the cylinders. This is one important differences. The other differences we have seen in the, we will see that in the case of point densities also there is a difference. Cylinder wire point density will be much more in comparison to Deferred. Deferred sheets are generally longer than cylinder. Since Deferred has to carry much thicker fiber layer on its surface, this point is to be noted that the fibers which are transferred to Deferred, these fibers have to be retained by the Deferred, and therefore, the height of the teeth on Deferred surface is generally much more than the cylinder, because they have to hold and retain lot of fibers to create an wave that we ultimately, when you strip the Deferred, we find a wave, but a wave consists of large number of fibers in the cross section. Further, it has to allow the air current generated by the cylinder to escape through the teeth, so as to facilitate fiber transfer and to improve the orientation on the Deferred. That is another reason why the Deferred tooth has to be little longer than the cylinder tooth. That is, we have to allow air current to pass through, and this will also help in transferring fibers from cylinder surface to Deferred surface. That means that the transfer process is both mechanical in nature, that is physical transfer because of the interaction of the teeth of cylinder and Deferred on the fibers, and is also aided by the air current which is generated. The other important point or parameter is the base width. Now, base width mainly influences basic point density. Lesser the width, more points can be accommodated across the width of the cylinder and Deferred, and correspondingly point density will increase. If we look at this, the equation that we have shown it earlier, you see the points per square inch, the denominator we have base width and also pitch. So, the base width is reduced, point density is going to increase. That means, we will be able to accommodate more wires per unit length across the width of the cylinder, and hence when you want to increase point density, we also reduce the base width of the individual wire points. Generally, the base width is 0.65 per cylinder and 0.70 to 0.9 for Deferred, but it may vary from manufacturer to manufacturers. If we go to the literature of the different manufacturers of the carding wires, then we will find that there is little differences are there between manufacturer to manufacturers, but on an average we can say the typical values are 0.65 for cylinder and 0.70 to 0.9 for Deferred. For high production card, it has been reduced to 0.5 mm, because we have to accommodate more teeth per unit area. When the production rate is very high, we have to tackle large number of fibers per unit time. So, when you have to tackle more fibers per unit time, this cylinder surface remains still same. There is a limit to the increase of speed of the cylinder. So, therefore, what we do that we want to increase the point density on the cylinder surface, and that is what can be done by reducing the base width of the wire on which the teeth are cut. So, point density, if we see now, point density is basically number of teeth per unit area. This also we have discussed earlier. It has a marked influence on carding intensity. However, point density and speeds needs to be considered together. This point is important here, that point density and speed needs to be considered together. it is the number of wire points available per unit time which is really important. A combination of low speed with high point density or high speed with low point density may be expected to give same results. So, depending upon the attainable speed by the cylinder on a given machine, we have to decide what should be the point density there, and accordingly we have to choose the wire point, because point density and speed has to be taken together. Various alternatives to increase point density. Alternative A already discussed, but I am going to repeat it again to make the things clear. A reduction in pitch would associate a decrease in h, that is height, while alpha and beta remains unchanged. This is one way of changing point density, that will reduce the pitch as well as height together without compromising on angle alpha, beta, gamma. Angles will remain same. The other alternative is to increase angle alpha or decrease beta, keeping point height same. If we do not want to compromise on height, we want to retain the same height, then we can change or play with alpha, beta, this alpha and this is beta. These two also we can play, that will also change the pitch and therefore point density also. So, point density wise, if we compare the two surfaces of cylinder and Deferred, then we find that point density on cylinder for cotton it can vary between 240 to 1000, Deferred it is 380 to 440. So, you see that on the Deferred the points are much less. For synthetics on cylinder it is typically 400 to 450, and for the Deferred it is 350 to 520. This is how the point densities are chosen, but exact values may vary from manufacturer to manufacturers, and depending upon the, it also depends upon the type of fibers we are going to process, whether cotton or synthetic. If cotton, was it stretchy cotton or not. So, all those points needs to be taken into account while deciding the exact value of point density on cylinder or Deferred. Now, this point which I told you earlier that this will take up later. Now, let us look into this point, relationship between grinding depth, carding angle, wedge angle and length of flat surface. The geometry of a typical tooth is shown here, and x is the grinding depth. When you grind the surface of the teeth of cylinder, let us say, then there is going to be a reduction in the height also. If we take a simple case where one typical tooth is shown, x is the grinding depth, L is the length of the land. So, if we grind it, as we grind, this will be the top surface of the teeth will look like flat. To begin also it is flat, it is not shown here, it is not really a pointed tip, actually it is also flat at the top, but if we grind it, this flat surface is going to be flattened more and more. So, let us look at this to understand what is, this is point A, this is point B, this is point C, and AC is x tan alpha plus gamma, BC is x tan alpha. So, what is L? L is basically length of the land. So, L is AC, L is basically AB, that means AC minus BC, and therefore, if we put the values of AC and BC, we get this. It is a function of grinding depth x and function of alpha and gamma. That is, this angle alpha, that is the carding angle, and the wedge angle gamma. These two are important in this particular case. If the carding angle alpha is increased, keeping beta same, you have to read it carefully, then angle gamma has to decrease, so that alpha plus gamma remains same to the earlier value. If we angle alpha, if we increase, then gamma has to decrease. Obviously, it has to decrease, but total summation of alpha plus gamma will remain same. Therefore, tan of alpha plus gamma is not going to change, because summation of alpha plus gamma will not going to change, but tan alpha value is going to increase as we increase alpha. That means, if we look at this equation L, then as we increase alpha, this part is going to be more, whereas this part is not going to change. X is going to increase as we go for more and more grinding depth. So, what will happen? The total value is going to increase, L is going to increase as we go for more and more grinding. Hence, for the same grinding depth, even if we keep x same and compare between two teeth, in the case of one tooth having lower value of alpha and other tooth having a greater value of alpha, then we will find that for the same grinding depth, increase in alpha, that is the tooth having higher value of alpha will reduces the length of the flat surface, L will reduce. A reduction in flat surface will reduce carding capacity. That is the situation that we will get, and this is how the length of this land is connected to grinding depth and the two important tooth parameters, which is alpha and gamma. Distribution of Slandered and Deferred wire points as they look like. So, here an impression of the wire points was taken on a piece of paper, that a piece of paper was pressed against the Deferred surface and against the Slandered surface, and this is the distribution of the wire point that we see here. It is very important to ensure that the channels do not form between the successive rows of wire points along the length directions. That is, we must not form channels. The way the points will be finally distributed, that there should not be a predominant line where we do not find any wire point. That we have to avoid. If it is there, if we find channels where no wire point exists, then the fibers will go and settle there, and these fibers will keep accumulating, and at some point of time they will be released and they will move as a cluster and they will go to the sliver as well without getting properly opened. Therefore, it is a constant effort by the machine manufacturers, especially the hard wire manufacturers, to ensure that channels are not formed on the surface of the Deferred or Slandered. So, distribution of the tips of the teeth are very important. Tooth leading edge. As I told you, the tip of the tooth is not really point, but there is a little land as shown here. The leading edge of the Slandered tooth is extremely important for efficient carding and nib removal. It should be straight and sharp. Look at this land, it is straight, and this here it is very sharp. The area below the leading edge are less important. Here these areas are less important. The land area gives support to the leading edge and provides the essential datum to allow a own leading edge to be corrected through grinding actions. The land area should be small as it keeps on increasing with every grinding operations, as we discussed earlier. As we grind, we go from this side to this side, obviously the land area will increase. A large land area reduces the ability of the tooth to penetrate into the tufts, and hence its penetrative power will decrease, and therefore there is a limit to which we can go for grinding, and once we reach that limit, we say that this particular wire points cannot be used, and we have to reclothe the carding, cylinder or Deferred. Tooth base, three types of bases can be seen: normal, locked and chained, as shown here. If you look at the bases, this is the base, these are the bases, these are the bases. The tooth base is slightly broader than the tooth point. This is necessary to adjust the number of wire points in the crosswise directions and provide adequate strength needed for winding the wire under tensions. See, these wire points are basically cut on a, as already discussed, is cut on a thin strip, and the strip is then wound on the cylinder, on the Deferred, on the Likert, and therefore, it has to bend. It should have little flexibility. At the same time, this would get lodged to each other, somehow they should be locked to each other, and therefore, strength is also required, since they have to be wound under tension, and hence the bottom part of the tooth has to be little wider. Normal profile for Likert and cylinder can be wound by forcing it into the groove cut into the surface of Likert or cylinder. That is, we cut grooves on the cylinder, and then we lodged these wires into those grooves, and when we are winding it, we are winding under tension. Pre-opening bars or carding segments. So, these segments also will have lot of teeths. Tooth points of these segments are designed in such a way that they do not need any cleaning. The way they are designed, the tufts and the tarr particles hardly adhere to it. Here the angles are chosen in such a way that nothing is going to be retained by those segments. The typical tooth densities are shown here for pre-opening bar and for carding segments. Depending upon type of cotton, you see fine cottons more, coarse cotton less. Fine means more fibers, they are finer in nature, we need more wire points per unit area. This is very obvious. Now, some facts to remember before we wind up. Coarser fibers are easy to individualize and therefore needs fewer points than finer fibers, that is, their point density could be little less. For a given fiber, high point density gives better results up to a certain point density level, beyond which the effect may be just opposite. This is due to the fact that fibers get so tightly packed into the cylinder clothing that transfer to Deferred becomes difficult, resulting no further individualization of fibers. For cotton, a high point density not concomitant to the level of trash present may cause the teeth to be loaded with particles in short time instead of releasing them to the flats. So, we have to be very careful in choosing the point density while processing cotton fibers. We have to remember what is the level of trash in the cotton, and accordingly you have to decide the point density. The other points are For Deferred, a long tooth with acute angle is preferred, since it ensures effective removal of fibers from the cylinder. Too acute angle makes the fiber transfer so efficient that recycling of fibers or cylinder, that is doubling effect, is reduced, resulting short term irregularity present in feed material to pass to the carded web, showing patchiness or sliver unevenness. Neb content in the sliver is also likely to be less. So, the angle is too acute in the case of Deferred, fiber transfer will be faster. As a result, cylinder load will go down. So, Neb content will be less, but the negative aspect is the doubling effect or recycling effect of the fiber layers on the cylinder is going to be less. On the contrary, a higher angle of the teeth reduces transfer of fibers on it, which will cause fiber load on cylinder to increase, and therefore, Neb generations. Hence, actual angle is a compromise between these two, and that is all. Thank you.